The hangar doors groan open, and Chief Engineer Takeshi Nakamura stops breathing. Before him sits the impossible, a B-29 Superfortress, intact. The aluminum skin gleams under harsh overhead lights, reflecting back a truth he doesn't want to see. The aircraft is massive, nearly 100 feet long, with a wingspan that stretches beyond the hangar walls. But size isn't what freezes him in place, it's the smell. Fresh machine oil, aviation fuel, American cigarettes. The bomber landed just 16 hours ago after sustaining heavy damage over WWII. The crew bailed out over China. But the aircraft, this magnificent, terrible machine, glided down into Japanese hands on November 11th, 1944. Nakamura's hands tremble as he approaches. He's been designing aircraft for Mitsubishi for 12 years. He knows every Japanese bomber and fighter inside out. He thinks he understands what modern aviation looks like. He understands nothing. Japan is losing. Nakamura knows this, though few will say it aloud. The Marianas have fallen. Saipan, Tinian, Guam. From these islands, American B-29s now rain fire on the home islands with near impunity. The raids grow more frequent, more devastating, more brazen. But why are they so unstoppable? Japanese interceptors struggle to reach the bomber's altitude. When they do, the B-29s shrug off cannon fire that would shred a B-17. They fly too fast for sustained pursuit. Their defensive armament turns the sky around them into a killing field. The military leadership demands answers. How do we stop them? How do we shoot them down? How do we build something comparable? Nakamura and his team of 30 engineers have been pulled from critical projects across Japan. Kawasaki Heavy Industries, Nakajima Aircraft, Mitsubishi. The best minds in Japanese aviation. Their orders are simple and impossible. Dissect this aircraft. Learn its secrets. Find its weaknesses. They have 1 month. Standing beneath the bomber's nose, Nakamura feels like an ancient warrior examining a rifle for the first time. The technological gap isn't years. It's a generation, maybe 2. The B-29 program began in 1940. By 1944, Boeing produced 1 complete aircraft every hour of every day. The bomber costs $750,000 per plane, more than most Japanese warships. Over 3,900 will eventually roll off assembly lines. Japan's most advanced bomber, the Mitsubishi Ki-67, entered service just months ago. It carries less than half the bomb load, flies 100 miles per hour slower, possesses none of the technological sophistication currently towering over Nakamura's team. He knows what he's about to discover will break something inside him. Still, he climbs the ladder toward the forward hatch. Takeshi Nakamura grew up in Nagoya, in a household that smelled perpetually of motor oil and ambition. His father repaired aircraft engines at the Mitsubishi plant. Young Takeshi would spend hours watching mechanics transform broken machinery into roaring life, learning that persistence could overcome any mechanical problem. He earned his engineering degree from Tokyo Imperial University in 1932, top of his class. The nation was modernizing rapidly, and aviation represented the future. Nakamura joined Mitsubishi with dreams of designing aircraft that would carry Japan into a new era. For 12 years, he's designed landing gear assemblies, wing structures, fuel systems. He's good at his work, maybe even brilliant. His colleagues call him the perfectionist, a nickname he secretly loves, because it means they respect his attention to detail. He has a wife, Yuki, and 2 daughters in Kobe. He hasn't seen them in 3 months. The work demands everything. The nation demands everything. At 42, Nakamura still believes in precision engineering as a form of patriotism. He believes Japanese craftsmanship, refined over centuries, can compete with American industrial might. He's about to learn how catastrophically wrong he is. The forward compartment smells of American coffee and leather. Nakamura runs his hand along the bombardier's station. The optical computing bomb sight alone represents technology Japan can't manufacture. The precision glass lenses, the gyroscopic stabilization, the mechanical computer that automatically calculates altitude, wind speed, aircraft velocity, and bomb trajectory. Japan's bomb sights require the operator to manually adjust for dozens of variables. This American device does it automatically. In seconds, he moves aft. His assistant, young Lieutenant Sato from Nakajima Aircraft, follows with a notebook, frantically sketching everything. "Sir," Sato whispers. "The instrument panel." Nakamura sees it. Rows of gauges, each one standardized, interchangeable, built to exact specifications with perfect repeatability. Japanese instruments vary slightly from factory to factory, sometimes from batch to batch. These are identical, perfect duplicates manufactured by the thousands. This is what industrial standardization looks like. But the instruments are just the beginning. The cockpit speaks of a design philosophy Nakamura has never encountered. Everything is arranged for crew efficiency. The pilot and co-pilot seats adjust smoothly on rails, a luxury Japanese fighters can't afford. The control yoke moves with hydraulic assistance. The throttle quadrant sits exactly where the pilot's hand naturally falls. Japanese aircraft are designed to specifications, then crews adapt to them. This aircraft was designed around the crew. "Take measurements of everything," Nakamura says quietly. "Every switch, every dial, every cable routing." He moves toward the flight engineer station and stops dead. The central fire control system, 5 remote-controlled turrets, 13 50 caliber machine guns, all aimed and fired from pressurized stations inside the aircraft. The gunners don't sit in open turrets, frozen and oxygen-starved at 30,000 feet. They sit in shirt sleeves, in heated comfort, aiming through computing sites that automatically calculate bullet trajectory and target lead. The system includes analog computers, sophisticated beyond anything Japan has attempted. The gunner simply tracks the target. The computer handles deflection, elevation, range compensation. Nakamura kneels before the central fire control panel, his hands hovering over the controls like a priest before a shrine. He's designed defensive armament systems. He knows the mathematics of ballistics. This system solves problems he didn't know could be solved. "Get the electrical engineers," he says. "All of them. Now." Over the next 3 days, the team strips away panels, traces wire bundles, photographs, everything. The discoveries multiply. The pressurization system. The entire crew compartment maintains sea-level pressure at 30,000 feet. Japanese pilots suck oxygen through crude masks, fighting hypoxia and frostbite on every high-altitude mission. These American crews fly in heated comfort, their performance uncompromised by altitude. The Wright R-3350 engines, each producing 2,200 horsepower, turbo supercharged to maintain power at altitude, fuel injected, self-sealing fuel tanks, automatic fire suppression. Japanese engineers have discussed these technologies. Boeing has implemented them as standard equipment. One engineer specializing in power plants takes 3 days examining a single engine. On the 4th day, Nakamura finds him sitting on the hangar floor, head in his hands. "The tolerances," the man says, "the manufacturing precision required for these cylinder assemblies. We couldn't achieve this in our best laboratory. They're mass-producing it." The radar system, an entire unit dedicated to radar operation. The AN/APQ-13 radar can map ground features in total darkness, through clouds, through weather. It displays a visual picture of terrain on a cathode ray tube screen. The radar operator can identify targets invisible to human eyes. Japan has crude radar sets. Nothing approaching this sophistication. Nothing integrated into the aircraft's combat systems. Nothing that transforms night and weather from obstacles into mere inconveniences. The radio equipment, multiple redundant communication systems, radio compass, identification friend or foe, IFF, transponders, liaison radio, command radio, each system ruggedized, miniaturized, reliable. Japanese radios are notoriously unreliable. Pilots joke that hand signals work better. These American systems are engineered for dependability. By the end of the first week, Nakamura's team has documented over 200 technical innovations they cannot replicate. By the second week, that number doubles. But here's where it gets really interesting. It's 2 a.m. on the 18th day of examination. Most of the team has left for the night. Nakamura sits in the B-29's pilot seat, hands on the controls, trying to understand. The aircraft weighs 4,500 pounds empty. With full fuel, bombs, and crew, it weighs over 133,000 pounds at takeoff. This is more than Japan's largest bomber fully loaded. Yet the B-29 flies at 350 miles per hour at 30,000 feet, for distances exceeding 3,000 miles. How? He's examined every system. He understands the components. But the whole represents something beyond the sum of parts. Lieutenant Sato approaches quietly. "Sir, you should rest." "I can't." Nakamura's voice cracks. "I keep trying to find where they compromised, where they cut corners to achieve this performance. There must be weaknesses, vulnerabilities we can exploit. And there are none." The words taste like poison. This aircraft represents a completely different approach to aviation engineering. We optimize individual components. They optimize the entire system. He gestures at the instrument panel. "Look at this electrical system. 3 separate 200-kilowatt generators. Any two can power the entire aircraft. Everything has backups. Redundancy built upon redundancy. Japanese aircraft save weight by making everything single point. 1 fuel pump, 1 hydraulic system, 1 electrical bus." "We're taught that excess is inefficient," Sato says softly. "Yes, but they're taught that failure is unacceptable." Nakamura stands, paces the cramped flight deck. "This aircraft doesn't just carry bombs. It carries its own machine shop. Complete tool sets, spare parts, everything needed to make field repairs. The crew can fix damage mid-mission." He opens a panel behind the pilot's seat. Inside, neatly organized spare fuses, relays, vacuum tubes, tools. Each item in its designated clip, secure but accessible. Our aircraft carry rice balls and prayer beads. Theirs carry spare radios. The observation sounds bitter. It is. But more than bitterness, Nakamura feels a growing horror, because he's starting to understand what this aircraft really represents. The Americans designed this system knowing they would lose aircraft. They built in redundancy because they accept that things will break, get damaged, fail. They engineered for survival in a hostile environment. They assumed problems and solved them in advance. Japanese design philosophy assumes perfect maintenance, perfect conditions, perfect execution. It assumes the warrior spirit will overcome material limitations. This American aircraft assumes nothing except that reality is harsh and preparation matters. "Sir," Sato says quietly, "the production analysis report you requested." Nakamura takes the folder. Intelligence estimates on American industrial capacity. Boeing plants in Wichita and Renton. Thousands of workers per facility. Assembly lines that never stop. 3-shift operations, 7 days a week. 1 B-29 every hour. His hands shake as he reads. Japan's entire aviation industry produced 28,180 aircraft in 1944, all types. Fighters, bombers, trainers, reconnaissance, everything. America will produce over 96,000 aircraft in 1944, including over 3,900 B-29s. And America is also building the world's largest navy and supplying its allies. and developing atomic weapons, though Nakamura doesn't know this yet. The mathematics are impossible. The industrial capacity is impossible. The technological sophistication is impossible. Yet here he sits, inside the impossible, with his hands on its controls. He thinks of his daughters in Kobe, the city where Mitsubishi builds ships and aircraft, a city that will certainly be targeted when the B-29 raids intensify. And they will intensify. This aircraft proves they will intensify. This machine represents industrial capacity Japan cannot match, cannot approach, cannot even properly comprehend. Nakamura stands abruptly, climbs out of the cockpit, walks to the hangar doors, and stares into the night sky. "Get the senior staff," he says. "All of them. Tomorrow morning. I need to make a full report." "What will you tell them, sir?" "Good question. The truth? That this aircraft proves Japan cannot win? That every engineer on this project now understands the war is unwinnable? That they've spent 3 weeks documenting their nation's inevitable defeat?" The briefing room feels like a tomb. 15 senior officers from the Army Air Force and Naval Air Force. Vice admirals, generals, men who have been demanding answers for months. Nakamura stands at the front with a pointer and 73 technical drawings. His mouth is dry. His collar feels too tight. "Gentlemen, after 3 weeks of comprehensive examination, I can report that the B-29 Superfortress represents a level of aviation technology approximately 5 to 7 years ahead of our current capabilities." The room erupts. Officers shouting questions, some angry, some disbelieving. A general stands. "Are you saying we cannot build a comparable aircraft?" "I'm saying we cannot build this aircraft." Nakamura's voice is steady. "We lack the precision manufacturing equipment. We lack the aluminum alloys. We lack the hydraulic systems technology. We lack the radar integration. We lack the production capacity. We lack the trained workforce. We lack everything." "Then what do you recommend?" The general's face is red. The words stick in Nakamura's throat. He thinks of his daughters, his colleagues, the young engineers who've spent 3 weeks documenting their nation's technological inadequacy. "I recommend we focus all efforts on defensive measures, improved high-altitude fighters, better radar early warning systems, dispersed manufacturing. These bombers will come in greater numbers. We cannot stop them. We can only attempt to minimize damage." An admiral slams his fist on the table. "This is defeatism." "This is engineering, sir." Nakamura meets his eyes. "I was asked to find weaknesses in this aircraft. I have found none that our current technology can exploit. I was asked to recommend countermeasures. I recommend we acknowledge reality." The briefing dissolves into arguments. Some officers refuse to believe the assessment. Others demand immediate crash programs to replicate key technologies. A few sit in silence, understanding what Nakamura is really saying. The war is over. Japan just hasn't admitted it yet. Within weeks, the report is classified. Buried, Nakamura is transferred to a factory designing improved flaps for outdated fighters. The B-29 is quietly returned to a secured facility. The engineers are told never to speak of what they learned. Some obey. Some quietly share their knowledge with colleagues. All of them understand. In March 1945, the firebombing of Tokyo kills over 100,000 people. B-29s flying at low altitude, free from effective opposition. In August, B-29s named Enola Gay and Boxcar drop atomic weapons on Hiroshima and Nagasaki. The war ends. Nakamura survives the war. His family survives in Kobe, though their home is destroyed in a raid. In the decades after surrender, he works rebuilding Japan's aviation industry. Eventually, he helps design components for civilian aircraft. In 1967, a Western journalist interviews him about the captured B-29. Nakamura is 75 years old. His hands shake with age, but his memory is sharp. "I'm often asked what I felt examining that aircraft," he says. "People expect me to say I was impressed, or intimidated, or angry." "What did you feel?" "Educated." He smiles sadly. "We were taught that Japanese engineering represented the pinnacle of refinement, that our emphasis on perfect craftsmanship and warrior spirit was superior to American mass production. That quality would triumph over quantity." He pauses, gathering thoughts. "That aircraft taught me that false choices are the most dangerous. Quality and quantity are not opposites. The Americans achieved both. They mass-produced excellence. They built to exacting standards at industrial scale. They created systems so robust that individual component failure was irrelevant." "When did you know the war was lost?" "In that hangar, day 18. I sat in the pilot's seat and understood that this aircraft represented a nation that had solved problems we didn't know existed. A nation that could wage war at a scale beyond our comprehension. A nation so wealthy it could afford to engineer redundancy into every system." "Did you report this to your superiors?" "I tried. They didn't want to hear it. Or couldn't hear it. Acknowledging the gap meant acknowledging we couldn't win. And if we couldn't win..." He trails off. "What do you do when your expertise tells you the cause is hopeless? When your skill reveals uncomfortable truths?" This question resonates beyond 1944 Japan. Engineers throughout history face moments when their expertise conflicts with political or military demands. When technical reality collides with ideological certainty. Some speak truth to power. Some stay silent. Some, like Nakamura, try to speak and are ignored. The captured B-29 revealed more than American technological superiority. It revealed the danger of building strategy on wishful thinking, of confusing determination with capability, of assuming spirit can overcome material reality. Japan's leadership chose to believe that fighting spirit, Bushido, could compensate for industrial inadequacy. They built this belief into their equipment, their tactics, their entire military philosophy. Light fighters prioritizing maneuverability over protection, minimal armor, no self-sealing fuel tanks, pilots flying until death because parachutes added weight. The B-29 represented a different philosophy, one that said, "Our pilots are valuable. Our crews matter. Engineer for their survival. Give them every advantage. Make the aircraft serve the human, not the reverse." This wasn't just better engineering. It was a fundamentally different value system expressed in aluminum and steel. Today, the restored B-29 Fifi flies at air shows. Spectators marvel at its size and sound. Aviation enthusiasts photograph its polished aluminum skin. Pilots describe the controls as surprisingly modern. But few understand what it meant to Nakamura and his team. Few grasped that moment in November 1944 when Japan's best engineers confronted the unwinnable mathematics of industrial war. Technology isn't neutral. It embodies the values, resources, and priorities of its creators. The B-29 carried more than bombs. It carried American industrial philosophy, manufacturing capacity, and a willingness to invest staggering resources in crew survival and mission success. Nakamura understood this. He saw his nation's defeat written in electrical schematics and hydraulic diagrams, in pressurization systems and fire control computers, in the simple fact that every single system had a backup. Sometimes the most important engineering discoveries aren't about building better machines. They're about recognizing the truth those machines reveal. The war would continue for 9 more months after Nakamura's examination. Hundreds of thousands would die. Cities would burn. An empire would collapse. But in that hangar, with his hands on the B-29's controls, one engineer already knew the ending. The mathematics were inescapable. The gap was unbridgeable. The outcome was certain. Sometimes courage means accepting what your expertise tells you, even when the truth is unbearable. Sometimes the most important question isn't, can we win? But, are we willing to see clearly? That lesson didn't die in 1945. It lives wherever expertise meets ideology, wherever technical reality conflicts with wishful thinking, wherever engineers must choose between comfortable lies and uncomfortable truths. What would you do in Nakamura's position? When your skills reveal the unwinnable war? When your expertise demands you speak truths no one wants to hear? The B-29 still asks that question, still waits for our answer.